Next up are rational functions. And as the name implies, it's something to do with ratios or quotients. Rational functions are functions of the form p over q, where both p and q of x are polynomials and the denominator cannot be 0 because, of course, we're not allowed to divide by 0. So for our very first rational function, let's take a look at the function 1 over x. What is the domain of f of x? So what are the numbers, the x values, that we are allowed to plug in for x? Notice, of course, that we have a denominator, which means that that cannot be 0, and therefore domain will not include 0 as a number. Everything else we can plug in and compute 1 over x as a value for the function. The next question is asking what are the x and the y intercepts of our function. So let's start with the y-intercept, and that is, of course, when we set x to be 0. Now, if I set x to be 0, I'm going to be computing 1 over 0, and of course we know that x equals 0 is not in our domain for precisely this reason. This value is undefined. So there are no y-intercepts. What about the x-intercepts? For x-intercepts, we're going to set y to be 0 and then try to solve for x. So we're setting 1 over x to be 0. And there are a number of ways to solve this equation. You can cross-multiply. You can also think of this as one whole fraction. The only way that a fraction is ever 0 is if the top of it is 0. But 1, of course, cannot be 0, which means that this too has no solutions. Which means that this function has no x and no y intercepts. Now clearly the values of x equals 0 and y equals 0 are problematic for this function, so let's maybe investigate this a little bit further. Taking a look at the form, it's 1 over x. It's really not surprising that 0 as an x and as a y value is a problem, because 1 over x, no matter what number I plug in, except for 0, which I cannot plug in altogether, no matter what number I plug in, this fraction can never become 0. However, if I plug in a very, very small number, the result will be huge, right? If I plug in, for example, 1/2, it's 1 over 1/2, which means that 1/2 will get flipped, and I'm going to get a 2. If I plug in 1 over a million, however many zeros that is, I'm going to get a million back. So the smaller the number I plug in into the x, the larger the number as the output will be. And then, of course, if I plug in a negative value for x, the outcome is going to be negative. So small input values for x will result in large output values for y. And that is an important property of this particular function. And so let's record this on the side. Small input values of x result in large output values of y, and they are going to be of the same sign. If small input value of x is positive, the output will be positive. If it's negative, the output will be negative. So this is what happens for small values of x, which means near the origin. What about the end behavior? So what happens as x approaches infinity or negative infinity? Let's write that down. So let's say x approaches infinity. Then y as 1 over x, I'm going to be dividing 1 by a very, very large number. So of course the result is going to be a very, very small number. It will be something close to 0. If I divide 1 by 1,000, it's going to be fairly small. If I divide by 1,000,000, it's going to be smaller still. And the larger the number on the bottom, the smaller the overall outcome. If x is a large negative number, so minus infinity, once again, y of course is 1 over x. If I plug in a very, very large negative number into x, I'm going to get a very, very small value for y, but it's going to be a very, very small negative number. So it's still going to be 0, but on the other side of it, right? So this 0 is positive because I'm plugging in a large positive value, and this 0 is negative because I'm going to be plugging in a large negative number. With all of this information at hand, let's sketch the graph of this function. Now, of course, the other way to sketch the graph of this function is to simply plug in points and look at the trends in the points. Now, I know from above that the domain is all x's not including 0, which means that the line for x equals 0 is not going to get crossed by the graph at any point. I also know that when I have small values of x, so as my x is near the origin somewhere, the result is large values of y, somewhere up there. And if I have large values of x, the result is small numbers of y, so somewhere there. Now I know that 1 over 1, for example, is of course just 1, so I can put that point there. And this will result in the familiar shape of this function's one branch. Same logic can apply to the negative side. If I plug in a small negative number, I'm going to get a large negative number. And if I apply a large negative number, I'm going to get a small negative number. So altogether, this graph will look something like this. This is the graph of 1 over x, right? So, of course, we notice a couple of things. The y-axis, or x equals 0, is a vertical asymptote. It will get approached by the graph, but never quite touching it, because my output here can never, my input here can never be actually 0. And same on the other hand, is no matter how big of a number I plug in for x, the output will be close to 0, but never quite be 0, which makes the x-axis a horizontal asymptote. This is the graph of 1 over x. The next two graphs we're asked to graph are going to be transformations of it. So once again, remember that if the transformation is applied directly within the function 2x, that's going to correspond to a horizontal shift. So this will mean that the graph is shifted 2 units to the right. Whereas if the transformation is applied to the outside of the function, so you can see the exact same function 1 over x, and then something added or subtracted to it, this corresponds to a vertical shift. So this will mean 2 units down. Okay? As you're sketching these graphs, keep in mind that the asymptotic behavior will move with them. So for 2 quick sketches here, let's take a look at what it means to shift everything down and everything to the right. So shifting everything to the right means that the asymptote will also shift 2 units to the right. And so now my graph will lie here, crossing now the actual y-axis, because x can now, take a look at the bottom, x can now be 0, but it cannot be 2. Here, everything got shifted down, including the horizontal asymptote. So the horizontal asymptote will now be here, and my graph will follow its vertical and horizontal asymptote. The vertical asymptote here did not change, so it will still be the y-axis. Keeping this in mind, let's take a look at the other 2 examples. So first I have x squared minus 4 divided by x minus 2, and I'm actually asked to sketch it for just the positive values of x, or non-negative values of x. Before we start sketching, let's take a look at the function and determine its domain. So the domain are all the possible x values that can be plugged in, and because there's a denominator, every time you encounter a rational function, you will have to start your consideration with domain. The denominator cannot be 0, which means that x cannot be equal to 2. Once we have that, we also notice that this function can actually be simplified, because this polynomial on the top can be factored out. So let's take a look at what we can do. X squared minus 4 all over x minus 2. Now the denominator, of course, can be factored into the difference of squares, x plus 2x minus 2. And then I notice that these 2 factors of x minus 2 cancel each other out because they're factors of the top and bottom. And so what I have left is just x plus 2. The graph of x plus 2 itself is simply a line, as we've seen earlier in this section. But now it's the line that cannot have a point at x equals 2. So this is going to be a line, and this is going to be a hole in that line. So let's sketch the corresponding graph. Note again that I'm only asked to actually sketch it for the positive values of x. So this is going to be a line of slope 1 with the y-intercept of 2. So I'm going to go through the point 2 here, and the slope is 1. So I have to keep that in mind. So my line is going to look something like this. Slope 1, intercept at 2. But again, I'm not allowed to have, my function is not defined at x equals 2, which means that at x equals 2 here, I have a hole in the function. Okay, this is going to be a hole. Great. Let's take a look at this other example, which is very similar. It's in fact kind of like the same function but flipped. So once again here, I'm going to start my discussion with first determining the domain, or all the allowable x values that I'm even allowed to use in this function. The denominator cannot be 0, which means that x squared minus 4 cannot be 0, which means that x squared cannot be equal to 4, which in turn means that x cannot be plus or minus 2. So note here that I have two exclusions now. After I've done that, I can notice here too that I can actually simplify the function. So let me rewrite that in a more simple form if possible. X squared minus 4 will, as before, turn into x minus 2, x plus 2. And once the factor of x minus 2 gets cancelled, I notice that what I'm going to have left is a factor of 1 on the top and a factor of x plus 2 on the bottom. So now I have this function that I have to draw, keeping in mind that my x is not allowed to be negative 2 and 2. Now this function, similarly to the function that we've just seen here, is actually the same as the base function 1 over x, but shifted 2 units to the left. So let's sketch that, and then we will identify where we have to have holes and where we have to have asymptotes. So it's going to be 1 over x shifted 2 units to the left, which means that my vertical asymptote will move to negative 2. And so my entire graph will then be a branch over here and a branch over here. Now once again, notice that I'm actually only asked to sketch it for x greater or equal than 0, so really I'm only sketching this piece. I'm going to include the entire picture for completion purposes though here. And then in terms of holes, I'm not allowed to have x equals negative 2. Well, that's just fine because that's still a vertical asymptote of this function. But now I'm also not allowed to have x equals 2, which will be this value right here. So at x equals 2, my graph here will have to have a hole. Notice that all of these are going to be rational functions because all of them have polynomial as a top and bottom. And as before, the first consideration in terms of rational functions are going to be the domain. So going through each one at a time, the domain is going to be all the x values that one can plug in, which means that you're going to have to exclude the values that will make the denominator equal to 0. So for function p of x here, we cannot have x squared minus 4 being 0, which means that x cannot be plus or minus 2. For the function q, that means that x squared plus 4x minus 5 cannot be 0. And so if I factor this out, this will turn into x minus 1, x plus 5, which cannot be 0. And again, the only time a product is 0 is if one of the factors is 0, which means that this implies that x cannot be equal to 1 or negative 5. And finally, for the function s of x, this guy right here, the bottom cannot be 0, so x squared plus 1 cannot be 0. But of course, this already has no solutions, because no matter what value I plug in for x, the outcome will be positive because it gets squared, and then you're going to add a 1 to it. So there's no way we're going to be able to ever get to 0. The other way to see it, of course, is to move 1 over to the left-hand side, and notice that x squared can never be equal to 1. Now there's no solutions to the denominator being 0, which means that all of the numbers are allowed. So in this case, the domain is all real numbers. Okay, so there are some rational functions where the denominator will not produce values of x that are not allowed, therefore resulting in the fact that the domain can still include every single real number. What are the x and y intercepts? So in order to do that, I'm only going to do this on the one example. For example, let's take function p of x, just to show you how to go through the logic of analyzing rational functions from the perspective of the intercepts. Let's first talk about the y-intercept, because as always that's the easier one. We set x to be 0, and we then can compute that y in this case will be 0 cubed plus 7 times 0 plus 0, so 0 on the top and minus 4 on the bottom. Now I'm not allowed to divide by 0, but I'm allowed to divide 0, right? If you have 0 apples, you're trying to divide them among your friends, everybody's going to get 0, so this is a total allowable operation. For the x-intercepts, we're going to have to set y to be 0, which means that now I'm considering x cubed plus 7x squared plus 6x all over x squared minus 4 being equal to 0. And as usual, there's more than one way to do this. You can cross multiply. This is essentially 0 over 0, so that's not going to get you much anywhere. But you can also multiply everything by x squared minus 4, keeping in mind that you've already excluded those numbers from the consideration. You can also think about the fact that a fraction will ever be 0 only if its top is 0, right? I'm not allowed to divide by 0, and the only other way to get 0 as the outcome is if the top is 0, which means that I have to have x cubed plus 7x squared plus 6x to be equal to 0. And now I'm going to try to factor this thing. I notice that I have a factor of x amongst all of the pieces, so I can take out one factor of x. And at this point I also notice that I can try to factor out this quadratic, and in this case it will be nice. It will be x plus 1 and x plus 6, which equals to 0, which will then, again, at every point produce one solution. Every bracket will give me one particular x-intercept for when these guys are 0 themselves. Okay, so this function, this p of x, has a y-intercept at 0 and x-intercept at 0, so it goes through the origin, minus 1 and minus 6. Okay, you can analyze the other two functions in a similar fashion. And in fact, thinking of the fraction being equal to 0 only when the top is 0 will immediately produce you the x-intercepts of 1 for this function right here and 0 for this function right here. The one thing you have to be careful about is, in fact, check for extraneous solutions. So in the case of q here, if the top is 0, that happens when x is equal to 1. But this is also the number that is not allowed to be in the domain. So you're going to have to watch out for whether or not the solutions that you've received here are going to be actually in the domain of the function. In the case of p of x, they all are. Do any of these functions have vertical asymptotes? And if so, what are they? The way we determine vertical asymptotes for rational functions is when the denominator is equal to 0, provided that this is not a whole. So unless it's a whole. So for example, in the case of p of x, the vertical asymptotes are going to be plus and minus 2, and it's not going to be a whole because neither of these are factors on the top. So neither of these points make the top of the rational function equal to 0. In the case of q of x, which is the one I'm going to go through here, so let me just go through q of x quickly. I'm going to have x minus 1 and x squared plus 4x minus 5. Now, seemingly, when the bottom is 0 is when I would have a vertical asymptote, but here I notice that the bottom can be factored out into x plus 5, x minus 1, which means that one of my factors of the bottom, and therefore potential vertical asymptotes, actually gets cancelled. So in this case, my function actually looks like 1 over x plus 5, and x equals 1 is not an asymptote, but rather a whole. Okay, so watch out for that. Don't just let the denominator be 0 and go on. Actually check to make sure that you did not get a hole in this case. The next question asks, do any of these have horizontal asymptotes? And if so, then what are they? Horizontal asymptotes is what happens to a function for large values of x, right? So let me just sketch a little quick sketch here. And let's say that I have an asymptote, a horizontal asymptote at some value of x. Okay, so let's say this is 3. What makes it a horizontal asymptote is if the graph of my function eventually approaches this value, right? That's what the term asymptote generally means, and you're going to discuss the concept of asymptotes much closer in calculus with much more rigorous definitions that you will develop using limits. However, for now, to simply use an intuitive understanding means that the function approaches this value and as close as possible, never quite getting there. In the case of vertical asymptotes, the value for when that occurs comes from, in terms of rational functions, when the denominator is 0, which really means that the value for x, like we've seen in the example before, for example, if this is the vertical asymptote, the function approaches it really, really closely, never gets there, and therefore can never actually touch or cross the vertical asymptote. With horizontal asymptotes, the situation is quite different. Your function has to approach it eventually as the value of x grows larger and larger. But that is an eventual behavior. What happens in the meantime does not affect whether or not this function is going to be a horizontal asymptote or not. So horizontal asymptote can get crossed by the function, and that's perfectly fine as long as the function eventually only approaches it. Okay? So the horizontal asymptotes are then, of course, dictated by the end behavior of the actual function, or for the values of x as they approach infinity and negative infinity. And this is something that we've discussed in terms of polynomials. For large values of x, whether positive or negative, we already know that a polynomial will be dominated by its leading term. All the other terms are essentially going to fade in comparison to how big and overwhelming the largest degree term is going to be. So for large values of x, only the largest powers will stay and everything else will not matter by comparison. So for large values of x, this function will approach x cubed over x squared, which we can of course simplify to be simply x. And if x is a large number, it's going to infinity, then this number alone is going to approach infinity. So for large values of x, this p of x simply approaches infinity. Okay, infinity is not a number, which means that this has no horizontal asymptotes. Take a look at the q of x. I'm going to have x minus 1 all over x squared plus 4x minus 5. I'm going to apply the same analysis to this here. So on top and on the bottom, only the highest degree terms will remain and everything else will not affect the ln n term behavior. So this function will then approach x divided by x squared, which of course, if I cancel out one of the x's, will be equal to 1 over x. And if x is a really, really large number, positive or negative, this value, 1 divided by a very, very large number, becomes a very, very small number, or 0, which means that for the case of the function q of x, the horizontal asymptote is 0. We will shortly see a case where the horizontal asymptote is also a number, and that's the same function as we called s above. But notice this rule here, because everything comes down to simply the leading terms is what we call them, the powers that are the highest degree on the top and on the bottom. You might remember from precalculus the rule that a rational function has a horizontal asymptote if the degree on the top is equal to the degree of the bottom, and then the horizontal asymptote is simply the ratio of the coefficients. If the degree of the top is smaller than the degree of the bottom, then the horizontal asymptote is 0. If the degree of the top is bigger than the degree of the bottom, then there's no horizontal asymptote. This is where this rule comes from, and I strongly encourage you to not remember it as a rule, but rather think of this leading term and behavior analysis every time, because this will be more helpful in the long run. Let's take a look at this function. That was the third function out of the 3 that we were given above to analyze. And let's not just analyze its behavior, but rather also sketch it. So first, let's maybe think of x and y intercepts. So the x-intercept is when the y is equal to 0. So I'm going to have 3x squared over x squared plus 1 is 0. And as I've said before, a fraction is only 0 if the top is 0, which means that in this case 3x squared has to be 0, which will give me the value of x equals 0. For the y-intercept, I'm going to have to set x equal to 0 and compute the corresponding y value. If x is 0, I'm going to get 0 on the bottom and 0 on the top and 1 on the bottom, which is perfectly fine, and that is equal to 0. For the vertical asymptotes, we've analyzed this function above, and the vertical asymptotes is when the bottom would have been 0, which happens for no values of x, so there are no vertical asymptotes. For horizontal asymptotes, we have to analyze the end behavior. So let's take a look at this function a little bit closer. 3x squared over x squared plus 1. I am going to take only the highest degree terms from each top and bottom. Now on top here, I don't have much of a choice. There's only one term, so I'm going to have to keep it as it's the only one. But on the bottom, I have a choice between x squared and 1. The higher power of x, of course, occurs in x squared. So this is the term that I'm going to keep. And then notice, because the powers were equal to begin with, that the x squares will cancel out, leaving me with only the value of 3. And that is then going to be my horizontal asymptote. I can also, using this power analysis and relating it to what we've talked about earlier, realize that I can analyze the near origin behavior using the same type of technique. So near the origin, recall that it's the smallest powers that are going to dominate, because if I raise a small number into a high degree, it becomes smaller still and therefore stops mattering as much. So now on the top, again, I don't have much of a choice, so I'm going to have to keep my 3x squared. But on the bottom, near the origin, I would like to keep the smaller power. The smaller power of x happens at 1, because that's when the power of x is 0. So I have 3x squared over 1, or 3x squared, which tells me that near the origin, my function behaves like 3x squared, like an upward-facing parabola, which is very useful when I'm trying to sketch things. So let's sketch what this function looks like. Notice that here it actually says to sketch for x greater or equal than 0. I'm going to sketch it for all values of x just to see how this actually works out. But these functions in particular, these types of functions, are useful in a lot of biological chemical applications, which is why the value of the variable is often restricted to be positive only, because you'll be talking about things like concentrations of various chemicals and whatnot. So what do we have from the information that we've retrieved here? We know that the x and y intercept is at the origin. We also know that it has no vertical asymptotes and the domain is all real numbers. The horizontal asymptote is at 3. So let's say this is going to correspond to y equals to 3. And I also finally know that near the origin, my function looks like 3x squared. So it's an upward-facing parabola near the origin. And then it has to somehow approach my horizontal asymptote. Now, what the analysis doesn't tell me so far is, just like here, does it cross the horizontal asymptote? Does the function increase and then decrease? So is this maybe what's happening? Or does it approach the horizontal asymptote from below and that's it? That is something that you guys are going to investigate in calculus. The best sketch that I can provide for now is something that looks like this, knowing full well that this function might very well be quadratic, as the analysis suggests near the origin, but then jump the asymptote and approach it from the top. Okay, it turns out that the simplest shape is the correct one, so this is in fact what this graph looks like. But in calculus, you will further confirm that this is indeed the shape and not something a little more intricate. So for just a quick review of the vertical and horizontal asymptotes, for a quick summary, let's just remind ourselves that vertical asymptotes of rational functions are when the denominator of the function is equal to 0, but you have to check to make sure that this value is not a whole. For horizontal asymptotes of rational functions, you're going to have to compare degrees of the polynomials on the top and bottom, so of numerator and denominator. And then, depending on which one of them is bigger, you will either have a horizontal asymptote or not. And once again, I cannot emphasize this enough. Please do not memorize the rule, because you might as well just remember it incorrectly and then panic during the test. Instead, use a leading term analysis in order to determine whether or not the given rational function has an asymptote or not. This is the end of Module 4. Please take a look at the Webwork assignment 4C, as well as a whole bunch of different exercises here to make sure that you can both work through a word problem, think about the domains, and sketch various rational functions.